We are, yo! That's right. I got a big voice so I can make myself heard. So we are going to be finishing our introduction to lists today. We're going to be going over why you should not be inserting or deleting from the middle of a vector. And then we're going to hit on something called double-ended queues and finish with a rather robust example of lists. And in between that, you're going to do a short code assessor problem that just gives you some practice using lists. Before we get started, I just want to again emphasize a couple things about what you should be doing when you're developing and testing your labs, because I'm still seeing the same kind of mistakes being made in the creation of your labs and the testing of them. So the first thing is, don't try to write your code all at once. Write a couple functions and then test them. And Dr. Plank gives you his source code for, in this lab, bitmap matrix editor. So you can tell which functions each of his commands calls. So when the simplest one is empty. To create a new matrix, he calls empty. Well, you can look at his source code, go to the if statement where he checks to see if the command you entered is empty, and you can see which functions he's calling. And then just write those functions and test them before you move on to your next things, which are probably going to be set and val. And the same thing, look at what his source code is calling, write those functions, nothing more, test them and move on. The second issue is that as soon as you write your code and compile it, I see a lot of you simply running the grade scripts. Those grade scripts are enormous and they're complicated. They are not good for debugging your code. Usually when someone comes in and says a grade script's not working, I try to get it down to something that's only a few lines long. And what I realize usually after I've done this is that if the student had simply tried a really simple example to begin with, they would have caught the bug. But instead, they have this enormous grade script and you waste a lot of time trying to narrow it down. And the grade scripts have 800 lines. It's really hard to debug one of his grade scripts. And the better thing to do is just start with small examples. He gives you the commands for his program editor. Run that program editor. Run it with some really simple commands and see there where your bugs are, because that's where they'll come out very quickly. And only after you think that you have gotten things working should you start running his grade scripts. Usually by the time you start running his grade scripts, 80 or 90% of your cases should work. Okay? So you may think, wow, I'm pressed for time, I can't do it this way. Believe me, the way I'm telling you to do it will save you time. So incremental development. When people say, what can I do to improve my coding habits? Incremental development. Don't write the whole program at once. Write just a small fraction of it. And two, do your own testing with your own small test cases. Don't just start running those grade scripts, because debugging those grade scripts is very difficult and time consuming. So those would be my two hints. Okay, so I also understand that Camille wasn't able to go over the Kino lab, which is the next lab in lab yesterday. I don't think that's a big deal because most of you are going to be focused on bit matrix until the weekend. And she is planning to create an online video describing the Kino lab, and hopefully that will be up by the time many of you are ready to turn to it. So I don't think it's a big issue that she wasn't able to get to the Kino lab on yesterday. And on Tuesday, I'll make sure that I ask to see if there's questions about the Kino lab, in case you have them. Okay, so as I said, today, 'Today, 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 ' the Dr. Planck's notes don't give you the whole list interface. And I forget, actually, I didn't check the book before I came to class. So there's a number of methods that he does show you. So you saw pushback, which adds elements to the end of a list. And then push front, which adds elements to the front of a list. And then there was insert, which took an iterator and a value. And where did it place the value? It inserts the value, but where? Pardon? Okay, that's not, so the answer was it inserts it where the iterator points. But you're right, the iterator points, let's say that you have 3, 8, 10, and I say insert, and I give the iterator points to 8. Where's it going to put, say, 5? Pardon? After. So let's take a vote. How many think after is the right answer? Oh, come on. Be bold and just that confident. That's right. Okay, and how many think before? Okay, so bold and confident was wrong. But sometimes it's right. So it goes before. Inserts the value before the value pointed to by the iterator. Okay, erase removes the value pointed to by the iterator. So you give erase an iterator. I actually should have put that there. So erase takes an iterator. And then there's several others that are very helpful. So oftentimes you want to remove from either the front or the back. So pop back will return, and delete last value in the list. Whoops. Pop front, as you might expect, does the same thing but at the front of the list. And then there's one more that's real helpful. It's remove. If I could spell it properly, remove value. And it will find and delete the first occurrence of that value. So the first occurrence of value from the list. So these are kind of the most handy of the functions that are associated with a list. Okay, and they're there for any type of value that a list holds. So these are the ones that I would try to memorize if I were you. So last time you saw some examples of using push back, push front, and insert. And what I wanted, where I stopped last time, was with an example using delete. So let's look at an example using delete. And actually, I guess I was the one who added this one, so, but in the notes, so you'll remember that I said a list is really bad for find. It takes a while to find elements in a list because you may have to search every element in the list. but it's really good for inserting things into the middle of a list and deleting things from a list. So with my delete example, what we're going to do is print out the elements of a list in sorted order. So here's an example list. And one algorithm, not going to claim it's the best one, but it is an algorithm that works, is to search through the entire list and find the smallest value. So if I want to print them in sorted order, I should print the smallest element first. So I walk through the list, I find that 1 is the smallest value, I print it, but what happens if I leave 1 in the list? What will happen on the next round if I leave 1 in the list? Pardon? It's going to print it again. So I have to delete 1 from the list. So, hence my ability to illustrate the delete operation. So I'll delete 1 from the list, and when I'm done deleting 1 from the list, I'll have 8, 2, and 10 left, and I'll have printed 1. So then again, I'll find the smallest element in the list, which is 2, and I'll delete it, so I'll print it, and delete it, leaving the list 8, 10. And again, I look for the smallest element, which is 8, delete it, leaving 10. So then when I search, there's only that one element 10 left. I print it, delete it, and my list is now empty and I can exit. Okay, so that's the algorithm. And note, again, a lot of you have trouble figuring out how to start a problem. Notice what I kind of did was figure out how to do it on paper before I'm even trying to code it. Now, I know I'm explaining it to you, but this is how I probably would do it on paper. I'd scan that list, find the smallest element, delete it, and then I would do that scan again. So now I have to translate it to code. Okay, so here's the algorithm for doing it. So I pretended that these are box sizes. So I'm just trying to print out or maybe arrange the boxes from smallest box to largest box. And what I need to do on each iteration is find the smallest box remaining in the list. So I can initialize min to be the first box in the list. Whatever that box is, that should be a valid value for min. So I initialize min to point to the first. So this is the first item in the list. And now what I'm going to do is simply go through my list, and I will keep updating min to always point to the smallest item. So here, this is just my iteration idiom, which you should get used to because you'll see it a lot for iterating through a collection of elements. And for each element in the list, I check to see whether that value I'm currently looking at is less than my current value for min. And if my value that I'm looking at is less than min, then I reset my min iterator to point to that smaller value. So when I finish the for loop, I know that once I'm done with this for loop, I know min points to the smallest element in the list. And in this case, this was the function I wrote. I was just trying to locate the minimum element. So you'll see that I first assign now the minimum element to my return value, then I erase min, and then I return the return value. Now, why not just do this? Instead of these three statements, why not just say box sizes dot erase min return min? Why not just do that instead? Yes, it's gone. After I erase min, it's no longer there. In fact, on some versions, min might actually get reset. It might still be there. What some versions will do is reset min to print to be the element before the deleted list element, in which case you would be returning the wrong one. No matter what, you'd pretty much be returning something that is garbage. We don't know what we would be returning because we already erased the value. So that's why this is no good, and you have to use the code on the left, where you first save the value and then you return it. So that was a good answer. So any questions about this find min? Pretty much like going through a vector, except now you're going through a list. Okay, and the rest of the code was here in sort.cpp, so the rest of it was simply to print out the list. I said while not lines.empty, because when the list is empty, I'm done looking at it, and then I see out whatever my minimum value is. And find min both returns the minimum value and deletes that minimum value from lines. So that's an example of delete. Whoops. Okay. So that's pretty much lists. Okay. It's a collection of elements. You can do operations on them, but inserting and deleting in the middle of the list are the big reasons you use a list. And then you have iterators that you can use to iterate through the list. Now, in the notes, or not in the notes, in the assigned readings, the book talked about something called an abstract data type. And a list, and actually a hash table as well, is an example of what we call an abstract data type. So an abstract data type simply lists a series of operations that it supports. So basically, an abstract data type is a collection of elements and a set of operations that can be performed on the elements. And it's called abstract because, first of all, we don't tell you the type of the elements. It could be anything, a string, an integer, some kind of class. So it's abstract because we haven't given you a concrete type, but it's also abstract because we don't tell you how it's implemented. It's a black box, just like how an alarm clock is implemented. An alarm clock gives you some functions like set the alarm, set the time, read the time, turn off the alarm, but you have no idea how the alarm clock is implemented. The inside is a black box. So that's kind of the same idea with an abstract data type. It is a black box that gives you, just says, look, it's a collection of elements, and here's the set of operations that can be performed on those elements. And that set of operations is called the API, or Application Programmer Interface. And as you learned on the test, some of you to your dismay, those are the public methods. Okay, equals set of operations you can perform. Set of public operations provided by the ADT. And then the way the programmer interacts with this ADT is through the public interface, through the API. They call them methods, and remember, typically these methods can either be mutator methods that change the values in the collection, or they can be accessor methods that access elements in the collection. What's hidden from the programmer is the way that abstract data type is implemented. You have no idea how the standard template library implements a list. it turns out there's multiple ways you could do it. One is with a vector, another is with an array, another is with what we call a linked data structure, which was introduced to you last week and which we'll consider again in another couple weeks. So there are multiple ways that you could actually implement a list, but we hide that implementation from the programmer so that the programmer's code does not become reliant on the way the abstract data type is implemented. And that way, we can always change the implementation of the abstract data type to some other form. So for example, maybe I implemented a list originally as an array, and then Dr. van der Zanden tells me how inefficient arrays and vectors are for implementing lists, and how much better linked data structures are. Well, if I'd made that array or vector implementation public, and someone's code had come to rely on using the array or the vector, then when I changed it to a linked list, their code would break. And that's bad, especially when perhaps this library is used by millions of people. You would break millions of programs if you change that internal implementation. That's why we make it private or protect it, so that the programmer cannot rely on your internal implementation. So get familiar with this term abstract data type. Get familiar with the term application programmer interface, because you will see these terms time and time again through your career as a computer science student and as a professional. Okay, so questions about that? Okay, so before we continue, let's have y'all do a little example in Code Assessor. So what I want you to do is go to CS102 Dev and, log in. And I want you to go to CS140, and you're going to find, it's in alphabetical order, so you're going to find a problem called list practice. I want you to take about 10 minutes and do that problem. All it's doing is giving you a little practice with push back, push front, insert, erase. And also, if you get done early, take a look at how I printed out the list. I provided the code for printing out the list. So you do a series of operations in the different boxes, and I have a little print list function that prints out the values of the list so you can see whether what you're doing is correct. So feel free to work with a friend. This isn't, I'm just going to, at the end of the class, or actually tomorrow at 12:30, check to see if you've done it. About 11:47, we'll pick up again. It is list practice is the name. So it's under CS, you go to CS102 Dev, make sure you go to CS102 Dev, then to the CS140, and it's list practice. Okay, and I'm putting up, if you don't have your computer for some reason, this is a set of operations I want you to do. But it's broken up into some boxes. And you're storing integers, by the way. So just so that you all know, I've seen this a couple of times, you cannot subtract integers from an iterator, and you cannot go from the back of the list if you're trying to insert. You have to start at the front of the list and move forward. That's for number 3. Okay, I gave you about 10 minutes. I know not all of you are done, but I am just going to go through the answers. So for inserting 3 at the beginning of the list, I just wanted you to use pushback. So pushback is the best way to insert something at the end of a list, and push front is the best way to insert something at the front of a list. So those are very simple commands. It got harder when I told you to insert 8 before 3. And I saw some of you try to go to the end of the list and then work your way back, which is a very natural thing to do, but C++ won't let you do it. While it will let you iterate in reverse through a list, the iterator that is passed to insert has to be a forward iterator. If you try to pass insert a reverse iterator, you'll get a compiler error message. Why? I'm not sure. It seems you should have been allowed to go backwards or forwards for insert, but it appears that you can only give insert a forward iterator, meaning you have to start at the front of the list to do the insertion. So that's why you see the lit equals new list begin. And then you can't add 1 or subtract 1. You can't say something like lit minus 1. That doesn't work. You have to say plus plus. Okay, you also can't say lit minus minus. Minus minus is not defined for iterators. I know that's a little confusing when you're using a reverse iterator, but you always use the increment operator to move one element ahead. So in this case, you were inserting before the 3. So your list at this point was 4 and 3. So the way to insert before 3 was to create a new lit traversal and make it point to 4, which is what this statement right here does. And then when I incremented lit plus plus, it made it point to 3. And because insert inserts before the iterator, that's what I wanted. So now I just said insert lit comma 8. So that got me the list 4, 8, and 3. Now I asked you to remove 4 from the list. And since 4 was the first element, you could have easily used pop front, which is what I was testing before I came to class. But I wanted you to get familiar with how to use erase. So given my instructions, what you actually had to do here was, use erase, and you could just simply pass it new list.begin because that will pass it an iterator. New list.begin returns an iterator that points to the first element of the list, which is 4. So then erase will erase that element, leaving you with the list 8 and 3. Okay? This is the one I want to take out. Then I asked you to add 10 to the back of the list, and push back is the easiest way to add something to the back of a list. And finally, I asked you to use remove, to remove 3 from the list. And that's very simple. You just call newList.remove. It finds the first occurrence of 3 and it deletes it, thus leaving 8 and 10. So questions about any of those operations? Now, just one question. Often they would be in a loop rather than just individually done like I did here, but I just wanted to get you some repetition using these functions. Yes?
It's just kind of a weird specific question, but with the let equals new list at begin, the let plus plus, I tried putting that before the pushback 3 and the push front 4, and it actually didn't work, but
right.
Since it's after the push.
Yes, it has to go after. The reason it can't go before, so if you say, if I put this, let's say I put these 2 statements before it, they're not, the list isn't, when you do that, the list is empty.
Okay, so you do that after you pass an element.
Right, exactly. That's why it wasn't. Yep, exactly. Gotcha. Okay, other question? Yes.
So that the remove command is just like you find and erase the.
Yes, so the remove command will find the element if it exists and erase it.
So my question is, if the list has like multiple of 3 values,
it will only find the first one.
Very first one
And remove it. Okay. Yes.
If our list was strings, we would pass a string to remove it,
Yep. So if the list was a list of strings and you passed a string to remove, it would locate the first one using string equality and remove the first occurrence. So it's real handy. Remove's super handy. And you're free to use it on the labs. Other questions? Yes.
So I assume there's no like find function for this.
There might be. I would have to search. I bet there is.
Because I'm wondering, like, if we have erased, then we need to find that element first, and then we erase that.
Yep. I did not check that before class, I have to admit. I was going through the list of things and it did, because this is what I wanted you to do, so I found those commands. I forgot to check to see if there's a find. You can do a Google search. I'm sure you would very quickly find out whether there's a find command. It seems completely likely. I would put the probability at like 90% that there's a find command because it's such a useful function. And then probably it would return a iterator to the element, and then you could probably just call erase. Okay, the other thing I wanted you to just quickly look at is how I printed out the list, because it was being printed out in a way that there was a space between each of the elements of the list. So for example, 3, a space 8, space 4. And I know that's the 4 and the 3 should be reversed. I'm just trying to show you there's a space. But what I'm seeing already, every semester, what I see when I ask you to put a space between each element is a lot of students put an extra space at the end of the line, which is wrong, especially with Dr. Planck's scripts. He doesn't put extra spaces at the ends of his line. And you get that when you basically say for each, say, element in some list, and if you just say cout element, and then you say a space, you end up putting a space at the end of the line, and that's wrong. So you got to get used to the fact that there's an idiom, a very good idiom for doing it, and it involves using a flag. So what you do is the flag lets you know whether you are processing the first element in the list or not. So if you are processing the first element in the list, you do not want so instead of putting a space after an element, we instead reconceive the problem as putting a space before an element. And it should be clear that there should be a space before every element but the first element in the list. So that's why we have our Boolean flag first. So when we iterate through the list, if it's the first element, we're not going to iterate through the list. We're going to iterate through the list. So when we iterate through the list, if it's the first element, we're not going to iterate through the list. So when we iterate through the list, if it's the first element, we're not going to iterate through the list. So when we iterate through the list, if it's the first element, we're not going to iterate through the list. So when we iterate through the list, if it's the first element, we're not going to iterate through the list. So when we iterate through the list, if it's the first element, we're not going to iterate through the list. So when we iterate through the list, if it's the first element, we're not going to iterate through the list. So when we iterate through the list, if it's the first element, we're not going to iterate through the list. So when we iterate through the list, if it's the first element, we're not going to iterate through the list. So when we iterate through the list, if it's the first element, we're not going to iter put a space, but we are going to set first defaults because every element after that is not the first element in the list. Otherwise, if it's not the first element, we want to print a space before we print the element. And this is the right way to think about printing out a set of elements in a list if they're going to be separated by a space. And that way you will not put an extra space at the end of the line and run afoul of Dr. Planck's scripts. Okay? So this is just a good idiom to learn. People say, how should I know it? You don't. It's something, someone clever invented way back when, and it's passed down through the generations by me telling you about it. And hoping that you write it down or write it down after class because it's part of the code assessor code, because it's an idiom that comes up again and again, especially in this course. So questions about that? Okay. So now, moving on. We've gone over lists. We've gone over whoops, did you need, just a sec, let me put it back up. I saw someone taking a picture. Did you get it? Got it? Okay. So we've gone over lists. We've gone over abstract data types. The next thing we want to go over is why it's such a horrible idea to insert into lists, or vectors rather, because you can insert into a vector just like you can insert into a list using exactly the same iterators of begin and an insert. Okay? I'm not going to show you the code. The reason I'm not going to show you the code is because it's such a horrific idea. I don't want you to learn the code. I want you, though, to understand why it's a really bad idea to insert into the middle of a vector. So if you have a vector, looks like this, and let's say 3, 6, 8, let's make it a little smaller so I don't have to write as much. And let's say I want to write 2 and I want to insert it at the beginning of the vector. Well, I can't overwrite 3. I need to, if I'm going to insert it at the beginning and preserve all my other values, what I first have to do is move every other value. And hopefully you learn from the test which item should we move first. If we're going to push 2, we need to start from the back, so we'll move 10 here, then we'll move 8 to here because 0, 1, 2, 3, 0, 1, 2, 3, 4. 10 used to occupy location 3, so before we put 8 into location 3, we need to move 10 to location 4. Then 6 goes into 2, and 3 goes into 1, and finally there's an open space, and we can put 2 in there. But the problem is we did 4 move operations. That's bad. A list doesn't involve 4 move operations when it inserts something at the front of a list. Okay, we'll see why in a couple weeks. For the time being, just take my word for it. It doesn't require more than 1 operation. But a vector in general, if you insert something at the beginning of a vector, insert at the front of a vector, requires n move operations if there are n elements. Okay, and Dr. Planck says something about what is called order n squared time. We're going to get to this so-called big O notation in another couple days, but it's a way of indicating roughly how long a program takes to execute. And in this case, what he's saying is if you insert a series of n elements into a vector and always use push front, it's going to take roughly n squared operations, n squared move operations to do that. And you can see that because the first insert requires 0 moves. There's nothing in the vector. The second insert requires 1 move. The third insert requires 2 moves, all the way up to the last insert, which is going to require n minus 1 moves. And you may or may not have seen this sequence before, but the sum of that is n times n minus 1 divided by 2, which is n squared over 2 minus n over 2. And if we just get rid of the constant, we have n squared. Well, that's pretty bad if n is large. If n is, say, 1,000, it means that we now need 10 to the third squared, or 10 to the 6th operations, which is 1,000,000. That's bad. Okay, in general, order n squared is a red flag that things are bad. Quadratics get big fast. And to illustrate his point, Dr. Planck did some timings using the time command. So if you want to time your commands, you can do them too. You simply put time before them. And the first file, he's inserting 10,000 elements. And in the second file, he is inserting 40,000 elements. And in the first two cases, he is using a list. And he's reversing a list, but he's using a list to do it. And you can see that the time doubles. That's not bad. It actually should quadruple because there's 4 times as many elements, but it's still pretty good. Now, the next two, he's using a vector. And it's a lot worse. First of all, 10,000 elements takes almost half a second as opposed to 1/100th of a second. It's 45 times longer using a vector. But it's even worse when you get up to 40,000. When you get to 40,000, it's now a full 7 seconds as opposed to 0.02 seconds. Now, it's something like 7,000 times slower, I believe. No, 700 times slower. A lot slower. And you can see that if it's n squared, this is roughly, I think, 100 million, and I think this is 1.6 billion. So this is 16 times longer, and in fact, that's about right. If you multiply 0.45 times 16, it's roughly 7. So you definitely do not want to be inserting into the middle or the front of a vector because it requires a whole bunch of move operations to make space for the new element. Same thing with erase. If you try to erase in the middle of a vector, let's say that I want it to erase 6 right here. I want to erase 6. That's going to create a hole. Okay? And what I'm going to have to do is I'm going to have to move 8 into the hole and then 10 into the hole vacated by 8. So again, with a delete operation in the middle or beginning of a vector, I'm going to have to do a whole bunch of move operations to get rid of the hole. So the bottom line is this. Do not insert or delete from the front or middle of a vector. Only add or delete from the end of a vector. Okay? And the reason is it's what we call an order n operation. Okay? It requires n move operations, where n is the number of elements in the vector. Whereas in a list, doing insert or delete from the front or middle is what we call an order 1 operation. It's constant time. It always just takes, in effect, one operation to perform. So this is something to remember because Dr. van der Zanden on exams likes to talk about efficiency. And if he gives you two pieces of code, like inserting into the middle of a vector and inserting into the middle of a list, I expect you to be able to tell me that inserting into the middle of a vector is less efficient because it requires order and move operations, which is a linear time operation, whereas inserting into the middle of a list is a constant time operation. So questions about why you should never ever insert into the middle or front of a vector. Okay. So moving on. We have something called Deques, which are a cross between a list and a vector. A Deques stands for double-ended queue. And it makes it efficient to insert either at the beginning or end, but not in the middle. So double-ended queues are efficient for inserts or deletes at the front or end of the queue. So a queue is a fancy word for list. But it's still not efficient for insertion or deletion in the middle. So it's still inefficient. Okay, are inefficient for inserts or deletes in the middle of the queue. And quite frankly, I don't use double-ended queues a whole lot, but they are in the notes, so we're just going to do a quick example with them. Okay, and the example is our good old friend reverse, where we want to reverse the lines in a file. So you'll remember if I have, for example, 1, 2, 3, 4 as my numbers in a file, if I start by putting them in the front, I will get 1, then I'll put 2, then I'll put 3, then I'll put 4, and then all I have to do is iterate through the list and print it out, and it will be reversed. And lo and behold, that's all this code does. You can see we include a deque. Now we tell C++ that the deque is storing strings. We use push front to push the strings onto the front. And then what is different about this line of code than a list? Because there is something different. It's not using pointers. It looks more like a vector, doesn't it? So in fact, they're doing something clever with vectors that you may or may not discuss in 302, but we're not going to discuss in this course. It's kind of complicated, but they actually are using a vector for this, but they're doing something really clever. It's basically using a rotating queue where if you get to the end, you go back to the beginning, but it requires some tricky coding. At any rate, you can see that accesses to deque elements use vector notation. So accesses to deque elements use vector notation. Okay? Can anyone think of a situation, a common situation that a DQ is very good for adding things at the back and removing things at the front. Okay, that comes up a lot in real world. What in the real world often has things added to at the back but removed from the front? Okay, playlists. Lines, right? Generally, we get in a line at the airline checking counter or the grocery store, movie theater. We go into the line at the back, and they remove us from the front. So DQs are really useful for modeling that real-world situation of lines. Like when you submit print jobs to a printer, that's what happens. They put it into a DQ. It puts the job, your print job, at the end, and when it's ready to print the next job, it removes it from the front. Oftentimes, when you submit a job to run, there's multiple processes executing on your computer. A very simple thing is to put your new command at the end of the queue of processes waiting to run, and eventually it will get its turn with the CPU. So DQs are really good for modeling or implementing lines. Good for implementing lines. Not a line of code, but a real-world line. Okay, I'll call it first in, first out line. Okay, you'll often see it referred to as FIFO for first in, first out. So they're good for implementing first in, first out lines. So you may get an opportunity at some point to use a DQ in the labs. Questions about DQs? Okay. So we're going to move on to the last thing today, which is an example from Topcoder of how you could use a list to count diamonds. So they came up with a pretty clever definition of a so-called diamond mine. So they call a string a diamond mine, and any pair of parentheses like this that forms a diamond is a diamond. But this is a magical diamond mine, because when you remove diamonds from the mine, you could create new diamonds. Okay? Which is kind of cool. So in this case, this is the first diamond. So when you remove it, you end up with a greater than, a less than, and now this is the next diamond. Okay, so we've mined this diamond and removed it. Now, this becomes the next diamond right here. So we mine it and remove it. And that, you can see, is going to leave us with, lo and behold, another diamond. See, right here. So we created another diamond by removing the first two diamonds. So now we remove this and this, and we're kind of out of diamonds. Our diamond mine is exhausted. But there's 3 diamonds in that string, 2 of which you could see at the outset, and 1 which was created by removing diamonds. Okay? This one, it should be pretty clear there's no diamonds in it. This one is odd. There's 9 diamonds, but only 1 evident. But the reason that there's 9 diamonds, hopefully you can see that as you remove the first diamond, a new diamond gets created right here. And then when you remove this diamond, yet another diamond gets created. And if you keep repeating that process, you would see that there's 9 diamonds. So we want to count the number of diamonds that can be produced by a string. And you see that I first didn't try to start coding. I tried to work it out by hand. And hopefully you might think, wow, this looks like a list could be used to implement this because he is deleting diamonds from the middle. Okay, in fact, if we were to use a list, how might it work? Well, what we might want to do is start looking at the beginning of the list, and we would need to look at wherever we were. If it was a left diamond, then if it's a less than sign, under what situations will we have a diamond? If the very next one is a right or a greater than sign. So we kind of are going to have two iterators, one that points to the current element and one that points to the next element of the list. You can see here we don't have a diamond in the first two elements because they're both less than. So what we're going to do is increment left so that it points to the next element, and we'll also increment right. And now do we have a diamond? The answer is yes, it's a diamond. So we are going to delete the two elements pointed to by left and right. And we will have to, before we do that, we need to move left, because if we delete what left points to, we won't be able to move it afterwards. So where should we move left in this case? To the left, over to here. Okay, so that's what we're going to do. So here we have left and right pointing there. Now he makes new left point just to the left of left, to right here. And now he deletes, can't quite there, let's see. You can see left and right are gone, and now he sets left to be equal to new left because he saved the position before left. So now he sets left to be equal to new left, and he can increment left to get right. And you can see that there is again a diamond. Now, when we delete left and right this time, it's a slightly different situation. Why is it different, Gavin? You're nodding your head.
Oh, because you can't go left anymore with the left one.
Very good. We can't go left anymore because there is no left element. So if we're deleting at the beginning of the list, then we have to set new left to be what will be the new first element of the list, which in this case is to the right of right. So there's a special case we have to deal with, which is we're deleting the first two elements of the list. Okay, so we delete the first two elements, and now we update left to point to the new first element of the list, and right doesn't give us a diamond, so we increment both left and right, and now we do have a diamond. So again, we make new left be just to the left of left, and we do our deletion. And now this is the only element of the list left, so it should be pretty clear we're going to be wrapping up. So again, before I do any code, I'm kind of figuring out, by using diagrams, how to solve the problem. I think this is a really good way to solve a problem. Instead of just blindly starting to write code, try to work it out on paper with diagrams first. And once you've kind of worked it out on paper, then you should have a better idea how to code it up. Okay, so here is Dr. Planck's code for doing that. And you can see it looks kind of nasty. So he is iterating through the size of the mine and pushing back all the characters onto his list. So we have a list of chars, and mine is the string. So initially we're just pushing all of the characters in mine onto our list. Then we set our number of diamonds to 0, and we set our left to the beginning of the list. And while left is not equal to the end of the list, we're going to kind of keep mining. So the first thing is, if left is equal to a right or greater than sign, that cannot be the start of a diamond. So we simply increment left in that case and move on. But if left is the else, means that left is a less than sign. So in that case, we set right equal to left and increment right so that it points to the next element. So if this is left, we want right to be 1 to the right of left, and these two pieces of code do that. Okay, well, first of all, we need to check if right is the end of the list, because if it is, it's no good. Okay, we can't do any comparison, it's invalid. It's pointing to the sentinel value in that case. But if it's not, okay, and if it is equal to the end, we know that there's no more diamonds in the list, so we return the number of diamonds. If we're not at the end of the list, then we check to see whether right is less than. If it's less than, it's no good. It's not a diamond, so again, we increment left. We could also have just set left equal to right. That would have worked equally well. But the else case, we have right being a greater than sign, and in that case, left points to a less than sign, and right points to a greater than sign. So we increment the number of diamonds. And if we found a diamond, we also need to delete left and right. But before we delete left and right, we need to update and set new left. So if left is the first element, the comment should be, if left is the first element of the list, then set left or set new left to be equal to right plus 1, which will be the new first element of the list. So that's what this code right here does. Otherwise, we are going to decrement. So actually, here I was wrong. You can decrement. Earlier I said you can't use the minus minus, but this is clearly decrementing. So we set new left equal to left, and then we decrement to get to the item before left. Then we can delete left and right and set left to be new left. Okay, I know I went through it a little quickly, but that really is a pretty literal translation of the diagram I went through. So take a look at this afterwards, because this is pretty neat code. Make sure you understand it. And next time we will start into the next topic. I'll finish up a couple things about lists, DQs, and vectors, and then we're going to move on to sets and maps.